Hello, and welcome back to Unconventional Computing, CS492 in fall 2024. We have some administrative matters to discuss. We will do that at the end of today's session. But first, let's continue learning about analog computing, about the theory, the mathematical theory of the general purpose analog computer devised by Claude Shannon, and the actual physical engineering device, the differential analyzer, as designed and built by Vannevar Bush. So let me recall what we learned about. We learned about differential equations. And differential equations are equations that involve the derivative of a function. So here you see examples like f prime, g prime, h prime. All these primes denote derivatives of a function. And u double prime means second derivative with respect to one variable. In this chapter, we consider functions of one variable, and this variable will be the time. So ordinary differential equations, fortunately, we can get away with ordinary differential equations. We don't need to learn about partial differential equations. That's an entirely different story and not tractable on the undergraduate level. And you've seen here examples. We discussed examples of differential equations. So the solution of a differential equation is a function. This is different from ordinary equations where the solution is a number, right? Quadratic equation solutions are numbers. And linear equation, the solutions are vectors, which means finitely many numbers. That's a system of linear equations. Here, the solution is a function, or if we consider systems of differential equations, like here, this is a system u prime equals v, and v prime equals minus u. So the solution of this system of differential equations is a vector of functions, a pair of functions u and v. And the solutions of differential equations tend to depend on a parameter. This parameter is called initial condition or boundary condition. So for example, here, the solution of these differential equations is constant times the exponential function. So e to the t, or 2 times e to the t, or 3 times e to the t are all solutions. We want a unique solution and therefore add this additional condition requiring that the solution must have value 1 at argument or time 0. And then the solution is unique. It's just e to the t without a constant factor. And same here, differential equation with additional condition. Differential equation with additional condition. And we saw that this differential equation is a special case of this differential equation. Namely, this one is simply the antiderivative. And this is a special case where y of t equals t to the k. And we consider this for different values of k, integers 3, 2, 1, 0, minus 1, and so on. Right. And we've classified these differential equations. This is a first order differential equation because it only involves f single prime. It's linear, no square root or multiplication, and it's homogeneous, no term that does not depend on f. The next example is also first order, also linear, but it's inhomogeneous because it involves a term that does not depend on h, the solution function we're looking for. So this is called inhomogeneous. This was an example of a second order non-linear homogeneous differential equation. This is a system, a first-order system. And we've seen that this is actually just a way of rewriting this differential equation. And that's a general technique. One can rewrite a second-order differential equation into a system of first-order differential equations, or higher-order differential equation into a higher-order system of first-order differential equations. So that's a kind of, how to say, like playing around with differential equations, reformulating one into another. That was an example of a nonlinear differential equation because it involves the square root. Then we reformulated this as a, right, so here's a differential equation, first order, with non-constant coefficient. This coefficient depends on time. And we've reformulated that as a system of first order differential equations with constant coefficient. That's another technique for kind of, what to say, playing around with differential equations, reformulating differential equation with non-constant coefficient as a system of differential equations with constant coefficient. And the benefit of constant coefficients is that the differential equation becomes time invariant. So when the coefficients do not depend on time, then it doesn't make much of a difference if we start the differential equation at time 0 or at time 1 or at time 15. And this is also called an autonomous differential equation, in this case system, because it doesn't depend on the time. Then we also considered an example of an implicit differential equation. Implicit because here all these equations were explicit. They had derivative on the left equal to something. Here the derivative is inside of the equation, and even it's inside of a square function. So that's an example of an implicit. Explicit differential equations all have the form derivative must be equal to something. So that's our recap of differential equations. And now I want to introduce a special type, a special class, a special form of differential equations. This is denoted with this equation prime. It's a system of differential equations. So it applies to several functions, uk, imagine it's u1, u2, and so on, up to un. So the solution will be an n-tuple, an n-dimensional vector of functions. Each function depends on one variable only, the time. So it's an explicit derivative on the left-hand side. And the right-hand side is this sum. And here we have some real coefficients, constants, c, I, j, k, indices, I, j, k. And here we have some other functions that are part of the solution, right? So ui, with I ranging from 0 to n, and derivatives of some other functions, uj, with j also ranging from 0 to n. So this is a special form of a system of differential equations, first-order differential equation. It's a first-order system, only involves first-order derivatives. It is nonlinear because there's a product, right, between two functions. It's not homogeneous, I'll say that in a minute, right? And it has constant coefficients, namely the coefficients are these c, I, j, k, which are real numbers, so they don't depend on time. Now, why is it inhomogeneous? Because I've added here, for conciseness reasons, one additional function which is not part of the solution. Namely, this is just the identity function. Imagine this to be a clock, an analog clock. At time t, the value is t, so it just shows how much time has elapsed since we started. And this is given the index u. And this is not part of the solution. We already know that part of the solution, but it occurs here on the right-hand side. For example, when j is equal to 0, we deliberately start here with 0. When j is equal to 0, that means it's the derivative of this function, and the derivative of this function is, of course, constant 1, right? So that's some inhomogeneity, because that doesn't depend on the other solution. Let me show you another example of a differential equation, which is also first order nonlinear with constant coefficient. Namely, this is a differential equation z prime equals exponential function of z. This is also nonlinear because it involves exponential function. It's actually homogeneous, and it has constant coefficients, so it's autonomous, because here hidden is the coefficient 1. But there's an important difference between these two types of differential equations. Namely, here the nonlinearity is polynomial. It's just product, basically something like a square. Whereas here the nonlinearity is not a polynomial, it's the exponential function, which is not a polynomial, right? And we're interested, well, actually, Shannon was interested in differential equations of this type, where the nonlinearity is only a polynomial and not something like the exponential function or logarithm function or other function. So whenever the nonlinearity is a polynomial, then we call this an algebraic differential equation, or here a system of algebraic differential equation. And such systems of algebraic differential equations tend to be important, and this is a main result of Claude Shannon. Now, if you're getting confused and maybe lost because this is beyond your traditional background of calculus 1 and 2 requirement for this course, and linear algebra 1 and 2, then don't worry. We only need some facts about such algebraic differential equations, and I'm going to report without proof, obviously, because the proof is very difficult. Some fact, classical. One part is due to Hölder, and the other is due to Hilbert, right? Two famous mathematicians. And this is already more than 100 years ago when they proved that the Riemann zeta function, which you probably know from the Riemann hypothesis, right? Number theory, prime number distributions, Riemann zeta function, one of the millennium problems, and the gamma function. Now, what is the gamma function? The gamma function is like the factorial, right? So remember factorial, 1 times 2 times 3 times 4 times 5 times 6 and so on. That's a factorial. And factorial of n is n times n minus 1 times n minus 2 and so on. But this only makes sense for natural numbers n, right? You cannot ask what is the factorial of 3 over 2, because 3 over 2 is not a natural number. But the gamma function is an analytic extension of that factorial function. So gamma function is a function that is defined on almost all real and in fact complex numbers. And for natural number arguments, it coincides with a factorial function, so it's an extension. So two famous functions, Riemann zeta function from the millennium problem, and gamma function, an extension, analytic extension of the factorial function. And Hölder and Hilbert proved that these two functions satisfy no equations of this form. So it's an impossibility result. They satisfy no algebraic equation system. And this is just something to keep in the back of your head. because later we will use that to conclude, along with Claude Shannon, that Vannevar Bush differential analyzer cannot compute these two functions. Differential analyzer can compute precisely the solutions to a system of algebraic differential equations. Every such system can be computed by a differential analyzer, and differential analyzer, whatever it computes, is such a solution to an algebraic differential equation, and therefore, by Holger and Hilbert, it follows that the differential analyzer cannot compute the Riemann zeta function nor the gamma function. So this is why we discuss it here briefly, but now you can safely forget it, because we will return to this later when we present Claude Shannon's theory. But for now, I want to take a brief break. Maybe I would like to ask you to do a quiz. Maybe you're not supposed to solve these differential equations, but I'm solving differential equations means finding a solution. But here I give you the solution, and I want you to simply verify that these are solutions. So already mentioned that the solution for differential equation f is the exponential function. So please verify that by calculating the derivative and comparing it with the original function, and verify that the value at 0 is 1. That's easy, right? And I want you to do the same for g with this function, and for h with this function, and for u and v with this function, and for w with this function, where c is an arbitrary real number. So this is where we take a break. I'm going to stop recording and give you time to do the calculations. You don't need to know anything about differential equation. This is just about calculating derivatives, which you of course know probably even from high school. Please write it down by hand and then scan it and send it by email. Okay, and here we are back, continuing with a lecture, maybe talking about Bush differential analyzer as a piece of advanced mechanical engineering. And I want to show you the ingenuity behind this differential analyzer. So to remind you, this is Vannevar Bush, born in 1890 and died in 1974, US citizen. He became a senator, right? And here you see him standing next to his differential analyzer. Actually, this was so successful analog computer that many of them were built and they were sold commercially, and they were used in the Second World War against Germany. So how does this work? You see here several rods, right? You see several units, and each unit has several rods, and the rods can be connected to each other with gears. Here you see some gear, right? Here you see some gear. And that's actually the basic data type, if you like, of the differential analyzer, is the angle of a rod. And a different rod is a different angle. So you can imagine each rod corresponds to a real variable. And the angle of that rod at a given time is the value of that analog variable. These rods can turn back and forth, and the angle at time A, at time t, that's the value. And the different rod V corresponds to different function of time. And you see already while we discussed differential equations and these function solutions, And right, I already showed you last time a video about the life of Vannevar Bush, very ambitious person who announced that he would complete a PhD at MIT in 1 year, and he beat himself, and it took him only 9 months. Just for comparison, for me, it took more than 5 years to get a PhD. And also we saw a video about the differential analyzer in operation at UCLA in California, right? As I emphasized, many of these devices were built and they were even sold commercially to other universities and to institutes. And these rods can be connected. That's kind of the programming. You could choose some of these rods and connect them. And there's one designated rod driving the entire machine. This is kind of like the engine, and the others then follow according to the gears which connect them to the one driving rod. We will denote the one driving rod with use naught. So the one driving rod rotates at a constant angular speed, so that its angle is basically the time. So this is the constant function that we discussed earlier when we talked about these differential equations. And yeah, like in computer science, the differential analyzer is built from very few basic primitives. In this case, it's only 3 primitive operations. And I want to review them for you. And the first is an ordinary gear, right? So here you see 2 rods connected with a gear to 2 wheels with different number of teeth. In this case, one wheel has 28 teeth, the large green one, and the other has 14 teeth, the small red one, so that each rotation of the green rod creates 2 rotations, twice as many rotations of the red rod. Or vice versa, if the red rod is the one driving, then the green one follows at half the angle and at half the angular velocity. And by choosing different number of teeth on the 2 gear wheels, one can thus create any kind of scaling. So here it's 2 to 1 or 1 to 2. But if you replace 28 teeth with maybe 27, it's going to be 14 over 27, or any other ratio between the 2 rods can be created. That's the first analog primitive of the differential analyzer. The second analog primitive is something that you probably know from maybe cars. In a car, there's one engine and it's driving the, let's say, back wheels or front wheels. But when you go into a curve with your car, then the outer wheel must rotate faster than the inner wheel. But if your engine is connected fixed to both wheels, then both wheels will rotate at the same speed, and you cannot go into a curve without causing the car to slide away in the curve. And that's why engineers have long ago invented very smart arrangement of gear wheels called the differential. Well, this has nothing to do with differentiation. Differential here means difference, the difference between the right wheel and the left wheel. And here you see the differential. So the large wheel is the one where the motor feeds in the force, and there's the left wheel connected to the red rod, and the right wheel is connected to the yellow one. And if both wheels, if the car is going straight, then both red and yellow will rotate at the same time. Namely, the green wheel will stay fixed, will not rotate, but it will, this blue box will rotate and thus transfer the power from the motor equally to the left and to the right. However, when going to the curve, maybe an extreme curve where the right wheel is standing still, and then the yellow wheel is rotating at twice the speed, right? Then this is accomplished by not only the blue box rotating, transferring energy from the motor to the yellow wheel, but also the green wheel will rotate, thus enabling the red wheel to stay fixed and the yellow wheel to rotate at twice the speed once because of the blue box rotating, and additionally because of the green wheel creating additional force on this. And I want to take a short intermission here and show you an animation of how that differential gear works in the car. Okay, yeah, so now we've seen how differential gear works. And the way it is used in the differential analysis, actually the opposite way. So mathematically, what happens is, let's denote the rotation of the engine, the blue wheel with W, the rotation of the left wheel with U, and the rotation of the right wheel with B. And then the power from the car gets distributed to both and left side, but not necessarily equally, right? But in total, it's going to be the power on the left and the right-hand side together will be equal to the power provided by the car. And now let's consider that in the opposite direction. Namely, suppose that U is driven and V is driven, then W rotates with a speed provided exactly by this equation. So that this device, the differential from a car, operated in the opposite way when U and V are driving rods, then it drives a third rod, W, according to this equation, which is basically addition. So that's an addition gate as an analog, more precisely because it's dividing by 2. This is an averaging gate. This is our second analog primitive used in building the boost differential analyzer. First is scaling, one rod rotating with a velocity given by another rod times the constant factor, and the other is adding the velocities of 2 rods, or more precisely taking the average velocity of 2 rods to drive a third rod. Yeah, addition has 2 inputs. It's binary, right? Binary operation. That's already our second primitive. And now to the third and last primitive. That's an integration gate. Now, how does that work? Here we have again 2 input. One input is the rod X that rotates at a certain speed. And the other input is Y. Y moves this wheel back and forth from the center to the border. Now, usually we suppose that this disk here is infinitely large. That's like a Turing machine is supposed to have infinitely long tape so that it can move this disk arbitrarily far out. Now what happens, the further out this disk, this wheel is, the faster it rotates, right? So this is kind of a different acceleration. close to the center, it rotates slowly, but depending on the rotation of this disk, right? So if this disk S rotates faster, and if Y is larger, then the output rod Z rotates faster. And if Y moves back and forth here, and if this also changes its speed, then the rotation of Z is described by this integral. Now, do you remember this integral? This is a Stieltjes integral. So it means integrating Y with respect to X, not with respect to T, as in Riemann integral, but with respect to X. And remember, we had a formula for that. And we'll return to that, but that's already all that is needed to build the Vannevar-Buss differential analyzer. Only these three primitives: scaling, addition, or averaging, right? We can convert averaging into addition by multiplying it with 2 using a gear scaling, right? This factor of 2. And this is basically integration. And with these 3 gears, Busch could solve all these algebraic differential equations, although he did not know that because only Claude Shannon proved how to do that. And one thing I want to point out here is there is no multiplication device. Can only add or average, not multiply. But Claude Shannon proved that it is still possible to express multiplication using a smart combination of this. And this is of course, that was a huge obstacle when kind of programming the machine and we wanted to multiply something. And but Claude Shannon demonstrated how to do that generically. But before moving on, let me show you another video demonstrating how this integrator works. So I'm gonna stop this again. Yes, so this is how the third analog primitive gate works, the integrator gate. And now all it takes is to combine them, and according to Shannon, combining them allows to calculate any solution to this differential algebraic equation. However, of course, there's a loss of power, right? And that's something that happens with any kind of computer that we saw before. In our digital computer, we need some external power source, right? Your PC has an external power plug. In chapter 0, we discussed cathode ray computers, tubes, right? What do these have? They need a heater and they need a cathode. And both need constant power, right? So switching power, but there must be some external power supply. When we discussed liquid computers, we considered this pressure amplifier. There's a control jet with low pressure, and there's a power stream with high pressure, and the control jet going from up or from down changes the direction of the power stream in this or this way, and thus kind of amplifies the power of the control jet by combining it with an external power stream, right? This or this. And the analog differential analyzer turns out to need a similar way of adding power, adding torque, it's called for rotational operation, adding torque to the rods. Of course, after several of these gates, scaling gate is not much of a problem. Differential gate is also not much of a problem, but the integrating gate is, remember that small wheel on the disk. There are no teeth on the disk. There are no teeth in this small wheel. It's impossible, right? Let's go back. Right here, there are no teeth. You cannot put teeth in here and matching teeth in the small wheel because the small wheel needs to move back and forth. So the torque, the power with which this output rod is rotating is very low. And if you consider that in turn driving another gear, another average, a differential, and driving another, right, again, a second integrator gate, then it will lose almost all of its power. So that was a main obstacle that faced by Vannevar Bush when implementing his idea, when building his machine. He needed some way to amplify the rotational power, the torque. And here's a device that people use on ships all the time. It's called a capstan. So this capstan is rotated by a powerful motor, not necessarily fast, but very powerful. And thus it can pull with very strong force, although the operator doesn't need to pull very, very strongly. Now, this is not to be confused with a winch. In a winch, the rope gets attached to the winch and then keeps pulling all the time. But the particular property of a capstan is if the operator does not pull, then the rope becomes loose and the capstan rotates without taking the rope. Whereas when the operator pulls, then the rope becomes tight and then it grips onto the capstan and the capstan pulls. So in this way, a capstan really amplifies the power of the operator, not just digitally, not just on and off, but when the operator pulls the rope more tightly, then it grabs, and when the operator makes the rope loose, then it starts slipping and less power is transferred. So now I want to show you an operation of a capstan in real life, a short demo, another video. That's ingenious, right? But it's only half of the story. For one thing, it needs to work in both directions. And also, it should reflect not just the power with which the operator pulls, but also the angle, right? We want to increase the power of a rotating rod and transfer the angle of the rotating rod to a new rod. And this is achieved by a so-called torque amplifier, which was a device, I think, even invented by Vannevar Bush. And this device is basically two capstans rotating in opposite direction combined. So this is one capstan, and this is another capstan, and they rotate in opposite directions. And this is the input arm, and this is the output arm. And it turns out that the output arm is always opposite to the input arm, but you need only very little force to move the input arm, and the output arm rotates synchronously, but with higher force, technically, with higher torque. That's why it's called torque amplifier. So let's now watch a demonstration of the torque amplifier. Yes, so this was the essential invention in order to build the differential analyzer, the torque amplifier. Okay. And yeah, time is already up. So next time, that is tomorrow, we will start discussing the mathematics of the differential analyzer and how that relates to algebraic differential equation systems. That's all for today. Thank you very much for your attention.